the how and when of using non-visible wavelengths. So to start, we really need to take a look at the light spectrum and understand where the wavelengths we're going to be focusing on today fall within the whole spectrum. The shortest wavelength you can have is X-ray. From there, we move to UV, which goes from about 100 to 400 nanometers. Then we move on to the visible wavelengths, which is what we've typically used in the past for machine vision applications. It's about 400 to 790, 800, kind of depends on the person. And then we step to infrared, which can be broken up into 4 categories as well. It goes from 850, you have NIR, which is near infrared. SWIR is shortwave infrared, medium wave infrared, and long wave infrared, which ends at about 14,000 nanometers. And then from there, you move on to microwaves, which is kind of used for X-ray machines, things like that. As you move from short wavelengths to long wavelengths, a couple things happen. First, the scattering ability of the wavelength decreases. So when a light hits a surface, the shorter wavelengths have a higher scattering rate than the longer wavelengths. So as we go, we start short, we scatter really well, and as we get longer, we don't scatter as well. But what does happen is the transmission rate increases. So these long wavelengths are able to pass through certain materials and remain unchanged. Therefore, they kind of make them appear invisible. That's how, IR light works, which we'll get into later on. And, X-rays and stuff, they're passing through unchanged until they hit something that does reflect the light back. So now that we kind of have an idea of how the wavelengths are, where they are in the spectrum, short versus long, and kind of what happens as you go from short to long wavelengths, how do we factor that into machine vision technology? Another thing to consider is different cameras will have a different spectral response, and we really want to focus on what happens at UV and IR. So this is an example just that I found off a manual from a random camera. Most cameras, all cameras should have a graph of this kind in their data sheet or manual where you can find out what the response is at certain wavelengths. The peak wavelength will be different for cameras, and if it's a color camera, it'll have 3 different peak wavelengths for each color. But you can see here that the UV light, it cuts off at 400, but you can still see UV. It's probably going to be around, 50, 40, 30%. And then it peaks at red wavelengths around 600, and then it drops down at around 1,000. So 950 is a good kind of standard IR wavelength we use, and you can see the response is only going to be about 15% compared to what you would get with red. So it is something to consider if you're using IR or UV light, that the light that you have won't go quite as far with your camera, so you're either going to need more lights or make those lights be brighter with overdriving or something like that. Sometimes it's, the exposure time of your camera is fine and you don't need extra light, but just keep it in mind that your light won't go as far with your standard machine vision cameras as it will for the visible spectrum. So the agenda that we're going to talk about today, we're talking about properties of UV light, comparing pure UV technology to UV technology, what happens if both of those work. Properties of infrared light, we call IR. We're going to compare using near infrared versus red light, the visible wavelength, and then properties of shortwave infrared or SWIR, and then comparing the SWIR to near IR when both of those work in the same situation as well. So what is UV light? So UV light is the wavelengths between 100 and 400 nanometers. UVA is from 320 to 400, UVB is 290 to 320, and UVC is 100 to 290. And then what are the uses for UV light? We see it mostly, in our real world applications as UV curing and machine vision applications. What is UV curing? It is the process of using a UV light to quickly dry or cure an ink, coating, adhesive, or something else, other materials. Its advantages are it's rapid curing and reduced energy consumption. But essentially what is happening is when the UV sensitive material is exposed to UV light, the photoinitiators absorb the light and are activated. And then that activation triggers a chemical reaction that leads to polymerization or cross-linking. So essentially what's happening is the molecules in the material form strong bonds with each other, transforming the material from a liquid or soft state to a solid state. And this is used in the printing industry, electronics, automotive, medical devices. A lot of places will UV cure, pieces together with a glue, and then they UV cure that glue to make it stick together, put an epoxy coating on, and UV cure that over everything. It's pretty common in a lot of industries. So what do we use the different wavelengths for in UV curing? What happens is kind of the same principle applies for the light spectrum. As we get longer wavelength, we can penetrate more and more. So UVC is good for if you're doing light top surface coatings. You just put an epoxy on and you're just curing that. UVB is for a little bit deeper penetration. Maybe you put a glue down and then you put something on top of it, and you want to cure that glue. You have to penetrate through the object first. And then UVA is used to cure deeper layers. CCS does offer UV curing options. We have a few different wavelengths: 265, 280, 300, 313, 365, 85, 295, and 405 nanometers. The geometry of the light right now is mostly custom orders, so there's not really a standard, get this ring light cured UV curing light. You kind of come to us with, hey, we need to cure something of this size, it needs to be this intensity and this wavelength, and we'll build you what you need. So if you do have any UV curing applications, please reach out to us and we'll help get you what you need. The next use of UV light is in the machine vision industry, and this is not necessarily new. It's been around for a long time. A lot of applications use UV, but the wavelengths are typically 365 to 405. We showed this camera spectral response, so no special camera is required, which can be a low-cost solution. But what UV light does is used to excite certain materials during inspections, and that's what we call fluorescence. Now, fluorescence is a phenomenon in which the wavelength of light returned from the shined object is longer than the wavelength of light shined. So we have our UV light shining down at 365 nanometers. Something in our sample has the property to get excited at that wavelength, and the light that it reflects off is going to be around 400 nanometers. So going into our camera, we have light shined 365 and light reflected 405 nanometers. Applications for this are to reveal invisible ink. That's kind of the easiest one because most of the time this ink will have a spec that says this fluoresces at 365, 395 nanometers, and you can just find a light that fits that nanometer. It can also be used to determine presence-absence of materials that fluoresce. Epoxy is a big one, adhesive inspection on labels, damp-proof insulated coating, glues and oil, lubricant, stuff like that. That tends to fluoresce as well. So really just testing if you're trying to see the difference between two different materials, especially if it's something like an adhesive or a lubricant. Try UV light. Sometimes it surprises you on if it will fluoresce or not. One thing we do utilize when we talk about UV light is using a UV cut filter. So what the UV cut filter does is it essentially blocks out any wavelengths shorter than about 400. So we know that the light shined is 365, the light reflected is above 400, and so we block out anything less than 365, so we just see what fluoresces. You can see kind of in the updated diagram that that filter blocks the UV, and now we just get that fluorescent light, so we get a more clear, higher contrast picture. Here's an example of looking at a diaper. There's a big strip that fluoresces in diapers. Without the UV cut filter, we can still see the strip is there pretty clearly, so this would be a good image. We are seeing some reflection of the 360 nanometers up in the corner. It's not necessarily a black and white photo. But once we add that UV cut filter, we don't see any of that reflection of the 365 nanometers. We just see what is fluorescing, so there's no need to hide or play with settings. It's just kind of a black or white. Is it present or is it not? So what do we need to consider when we have a UV light? In the past webinars and stuff, we've just talked about, use UV, it works really well, but UV can be damaging in a lot of ways. So extra precautions have to be taken if you use a UV light versus a visible light. First, you should shroud the machine. Try designing the machine so it's closed. Put a shrouding around the inspection stage because, as I said, UV light can be damaging to operators. If you cannot fully shroud the machine and close it off, then any operator standing nearby needs to have proper PPE. You need to have eye protection and exposed skin protection at all times that the light is on. Other lighting options, UV often requires using a UV cut filter. Sometimes you don't always have to use it, but more often than not, it will improve your image. You also cannot use polarizers or other optical accessories on UV light. If you try to put a diffuser on a UV light, you will have, over time, that diffuser will cure and kind of become more or less diffuse and eventually ruin the output of the light. So if you buy a UV light, it's going to have a glass protectant, and unless you buy a specific UV polarizer, if the company has one, you can't just add any old plastic polarizer to it. And then another thing is UV lights are not going to be as intense as the visible wavelengths. The LEDs themselves are just not as powerful enough. And then if you factor in the camera spectral response, it might take 2 to 4 more lights than a standard wavelength would give you to get the same results. And then the lighting geometry, UV does not have as many form factors as visible lighting, kind of because of the UV curing properties. We can't use it to make an LFXV, for example, or a coaxial light. That being said, typically when you're doing UV, you kind of just need the wavelength. You're just shining a bar light down to an area and letting the fluorescence do its job, so you don't necessarily need the form factors that we would consider for more high precision applications. So they kind of don't exist because they don't have to, but they also don't exist, so it's something to consider. If a coaxial light solves your application, then try and find a coaxial light in the visible length that solves it instead of in the UV length. So ultraviolet UV versus pure UV, and what is pure UV technology? So pure UV technology, which we just abbreviate as PUV, what it does is it's a special technology that FE-Lux lights have, where part of the spectrum of the 365 light will pass through the UV cut filter. And what happens is the pure UV technology can remove kind of the tail of what can get through that filter because there's a slight overlap. And so we get a more high resolution, high contrast image. And this really only comes into play or only occurs in applications that have a lot of glare. So you can see in this application, we have a UV light being shined onto a very reflective material with a barcode that fluoresces. So what we're capturing here is a 365 nanometer light shined and the fluorescence. When we add a UV cut filter, we're blocking out that light shined, but we're still getting some reflection. In most applications that aren't as reflective, this doesn't really happen. That UV cut filter fully cuts out all of that 365 nanometers. But sometimes it doesn't. Really reflective material. Can we still read this barcode? Probably, but having a more repeatable image is always going to be the goal. So when we take this application and we use pure UV technology with it, so we've got a pure UV bar light with the UV cut filter, we're cutting out that little tail that was passing through the filter is no longer passing through anymore. So now all we're seeing is the fluorescence. There's no light shined wavelengths being sent through to the camera. So something to kind of keep in mind if you're coming across a lot of UV applications. If you think any of them have high glare, pure UV technology is going to be the best answer. So what's the overlap between these two technologies? All pure UV applications are part of the UV applications. You're never going to have pure UV application that's not also just UV. But within UV applications, you have applications that have really high glare, and the pure UV technology is going to be the best for that solution. But sometimes, you get the same results. So this is an example of invisible ink on a bottle of Prosecco. When you use pure UV with the UV cut filter, it looks, good, high contrast image. And when you use UV light, just a standard UV light with UV cut filter, you have the same image. So sometimes, in the image I showed just before this, there was a drastic change from pure UV to UV light, but sometimes the change isn't that different. So when it's the same, the result with pure UV or UV is the same, how do we choose which option to use? The first thing to consider is the lighting geometry. Pure UV is limited to only bar lights and a spotlight and can only be 365 nanometers. So if you need something that's a ring light or a different wavelength, you just can't use the pure UV technology. The other thing to consider is the price. Pure UV is slightly more expensive than the standard FE-Lux UV. So it's not a crazy amount by any means, but there is just something to note. So when it comes to options for your applications, what form factors can you get all of these wavelengths in? Here's just kind of a little bit of a breakdown. So CCS and FE-Lux both have their options of UV lights. So CCS has the UV3 line, which has ring lights, bar lights, spotlights, and line lights, and then the visible light line, which is 385, 395, and 405 nanometers. So the geometry of these two is the same, it's just the different wavelengths you can get, and they don't come with the pure UV technology. The FE-Lux lines, you can get bar lights, ring lights, spotlights, and a line light. The FE Flex, the FE Ring, and the FE Sharp can come 365 nanometers, but only the FE Flex and the FE Sharp have the pure UV technology. Otherwise, they all come in 405 nanometers, but none of them have pure UV besides these two. So this is kind of an easy breakdown of, what light, what do I need, what company should I buy it from, can it come in, I need a line UV light. Okay, will we get the FE line or the CCS line kind of thing. So if you're looking at using a UV light and you're not sure which direction to go, this can be a nice guide for you. Okay, moving on from UV, what is near infrared or what we call IR light? So near infrared is the wavelengths from 780 to about 1,000 nanometers. Same with UV, there's no special camera required, but again, keep in mind that the spectral response of the camera is not going to be as high. The examples that we have are you can transmit through opaque materials, you can do surface inspections by removing print or something along those lines. You can use it in combination with the filter to remove ambient daylight or as non-visible lights that don't disturb operators if it doesn't change the resulting image. Other application examples we have are looking at foreign material in soy sauce. So when we use a white backlight, the white light hits the soy sauce and is blocked, so it doesn't reach through to the camera. And so since no light passes through, it appears dark to the camera. But with an IR light, 940 nanometers, that wavelength is able to pass through the soy sauce and remain unchanged and reach our camera. So therefore, our camera doesn't see that dark color. However, the foreign material inside is blocking that light, and we can really see the presence or absence of that foreign material. So if you wanted to do a fill level inspection on soy sauce, you would not want to use IR light, you'd use white. But if you wanted to do an inspection of making sure there's no contaminants, then you would use IR. On the same side, we're using it to remove print. There's a little tiny pinhole where in the visible light you wouldn't be able to detect it or distinguish it from the print on the package. But with IR light, that wavelength is passing through the print unchanged, but reflecting off of the plastic material. So therefore, it's essentially removing the print, but still showing the pinhole and the plastic packaging. So red versus near infrared, because they're pretty close on the spectrum, the lighting spectrum, they're right next to each other. So red light, we use it to create contrast on a sample with a monochrome camera. I mean, you can just use it if it, just solves the application, but a lot of times we purposefully use red when we want to highlight the red versus the blue piece on the sample. A red light with a red sample with a red light will lighten, and a red sample with the blue light will darken. So we use the red light if we want to create contrast. Versus the NIR light, we're using it to purposefully remove color or text from a sample to highlight a pinhole, for example, or just make each sample consistent. I've used it in applications where we had 5 different samples come through that were all slightly different color, but we didn't want to change the program much, so we used IR light and made them all kind of a basic gray. The overlap that can occur is when the red light creates the same contrast the way the IR light creates the contrast. We've seen this with red text on a white background. You can either use the red light to lighten that red text and make it appear white, or you can use IR light, might possibly pass through that red text and remove it as well. Or using black text on a white background, the red and if the text isn't eliminated by the IR light, it's going to remain black, and the red light's not going to darken or lighten black at all, so you're kind of going to remain with black on white contrast, or using it on metal, silver, white, kind of anything that doesn't really change due to color, but an IR light won't change either. So examples, this one's we've kind of used before a lot because it does a good job of showing, red and yellow packaging with red light removes that print. Essentially, you can faintly see it, but you can really see the perforation, and that would be really clear. With an IR light, we get the same result. It's passing through the print on the box and just showing the packaging and that perforation. So in this scenario, both lights would be a good application. In this example, we're looking at a battery, and it's a silver battery with pinhole or with punctures in it. So we use a coaxial light at a high working distance to optimize our columnization. And you can see that the red light and the IR light have the same results. So while we're not necessarily using the color, the wavelengths are having the same results as they did when we were utilizing the color. So if both applications work, how do we choose between NIR or IR light and red light? One thing is human presence. Red light, especially if it's strobing, might bother workers nearby. So if you can pick between the two and there's going to be an operator standing right there, using IR light, they won't see it. It won't affect them performing any of their operator duties. Lighting geometry. IR lights have many of the direct diffuse illumination options, form factors, etc. as red light. So you kind of can have both, whatever you want. You can have it in whatever form factor you want. The price, IR lights do have a slightly higher cost. And then another consideration is the camera sensitivity is higher at red wavelengths versus the IR. If you remember in the beginning, red was 100% response and IR was about 15. So if you're struggling for light in this situation, you might want to pick red over IR. So more options for your applications, what CCS and FELux offer. For CCS, all lights come in red. There are a few exceptions of our collimated coaxial and backlights just come in white, but everything else comes in red. FELux, all of their lights come in red. In CCS, you can get any form factor in IR, not any series. But any form, ring, dome, flat dome, backlight, bar light can all come in IR. And we'll have wavelengths 850, 860, 940, or 950, depending on the product. And then in FELux, all FELux products come in 850 nanometers as well. So there are definitely a lot of options if you're choosing IR lights of which kind do you want. Okay, what is shortwave infrared light, or what we call SWIR? So properties of SWIR light, it goes from about 1,000 nanometers to 2,000 nanometers. And this has really high penetrating properties. So it's really able to pass through and remain unchanged, but reflect off other materials. Unlike the mid-wave infrared lights and the long-wave infrared lights, which is emitted from an object itself, SWIR light is similar to visible light in that the photons are reflected or absorbed by an object. So it provides the strong contrast needed for high resolution imaging. So that's why we don't use mid-wave MIR or LWIR light in machine vision applications. Applications that we have for this are to differentiate between materials. Sometimes it'll make one material appear dark, another one appear light, even though to the visible eye and to visible wavelengths or IR light even, they appear the same. They'll kind of be different with SWIR. It can reveal hidden elements like water in rice, moisture levels. You can see through objects like plastic, silicone that other wavelengths aren't able to penetrate. And you can see the wavelength is important. It's not necessarily just, oh, pick any wavelength in SWIR and it will work. Sometimes there's a critical wavelength that will solve the application. In these pictures here, we have a metal ring looking through kind of a plastic top. With the IR, you can kind of see the metal ring, the 940 nanometers. At 1200, we're getting better. You could see that it's there. This would probably work, but not be the best. But at 1450, we're really getting that reflection off of that metal ring and really penetrating through that plastic cover. So when you're testing SWIR, it is important to make sure to test every wavelength. Other application examples are fill level. So this is a backlight with a coffee can. No other light is going to be able to give a clear level, fill level so clear. And wafer inspection, very common for this. This is actually looking at the front side of a wafer that to the visible eye appears, totally just plain, but the SWIR light is able to see through all of the layers and see what's on the back by looking at the front. So using SWIR and wafer inspection is a very, very common application. So what happens when we compare IR lights to shortwave infrared lights when we have an application where maybe both of them work? An example of this would be this sugar packet right here. So we have the IR light is removing the sweet and low print on the packet and showing that there is sugar in the outside packets, but there's no sugar in the middle packet. The SWIR, we're getting the same result. It's removing that print and showing the presence-absence of the sugar on the outside. So in this scenario, both applications work. What do we do next? And what's the overlap? We have those two applications, those two solutions. Again, with the IR light, we're removing color, text, print, trying to make a sample consistent, highlight pinholes. It does work for fill level if we're penetrating through a plastic. But SWIR light is really the best at penetrating through certain types of materials that are opaque under visible light or highlighting differences in plastic, cloth, paper, etc. So the overlap is just going to be the samples that have the same reflection in IR light and SWIR light and have the same results. So if we have the solution where IR light and SWIR lights have the same result, how do we choose? How do we pick? Well, long story short, if you have the option between IR and SWIR, just use IR. It's going to come in more profiles, but SWIR does come in a bar light, dome light, ring light, spotlight, and backlight, and line. But IR comes in a lot more, flat dome, standard dome lights, things like that. And then the price, the SWIR lighting and the components are much more expensive than IR lights. The camera and lens is more expensive, the lights are more expensive. So if you can get away with using IR, you'll save a lot of money. And then kind of other components, SWIR does require special equipment. You cannot use a SWIR light on a standard camera. You have to have a special designated camera with the right sensor in it and lens. Technically, you can get away not using a SWIR lens, but your image quality won't be as good. We still recommend using a SWIR lens. So can SWIR solve everything? No, unfortunately it cannot. Here's an example where there's a pineapple that had bruises on either side, and we wanted to essentially determine if a SWIR light could see the moisture content and where the bruises would have a higher moisture content, and therefore we could detect the bruise on fruit. with all the wavelengths we had available, there was no way to see the moisture content. It just wasn't a successful application. We even took it to an X-ray machine to see if that, we just needed to penetrate more. But even with an X-ray machine, we weren't able to see the moisture content or distinguish it in this image. So sometimes applications just aren't solvable, and SWIR doesn't solve everything. That being said, if you think you have a SWIR application, always, always, always try it. SWIR is still new to the machine vision industry, so we really can't say, yes, it'll definitely work until we test it. Unfortunately, people want to just say, oh, can you just, tell me what wavelength and I'll get that one. And no, we really can't. Not only do we not know which wavelength will work, we don't know if any wavelength will work. So it's really important that if you think SWIR will solve an application, to try it out before purchasing anything, because as I said before, SWIR can be expensive. I do recommend having a lighting manufacturer evaluate it before you buy the components. I kind of say this because, a camera manufacturer might have some SWIR lights, but it's easier for a lighting manufacturer who does have the SWIR lights to get a SWIR camera. So, for example, we have a SWIR camera and a variety of lights to test our applications. So when we evaluate SWIR applications, we fill out the same evaluation form where we figure out what your setup is and try and recreate that as best we can. And then we ask you to send the sample to us, and we'll test the wavelengths that we have. We have bar lights in every wavelength we offer that are 100 millimeters long. And with this, it's not the perfect setup, but we're able to see, this wavelength works. This one doesn't, etc. And then from there, we kind of pick the form factor that we'll need. But the initial part of testing is testing for the wavelength rather than the form factor, which is kind of the opposite as we do for, visible applications. One thing I do want to highlight is we do SWIR testing in-house only, meaning we don't send our lights or our camera out to customers to do their own testing. Not everyone's as careful with our lights as we are, and since they're expensive, we don't want them damaged or lost or not returned. So if you want us to test your applications, we are 100% more than happy, but you'll have to send us your sample for us to do our own testing. And then we'll send you the report and your sample back. So options that you can get with SWIR lights, CCS and FELux have the same wavelengths available. CCS has more form factors, bar, ring, back dome, spot, and line lights, but they are in a smaller size. So with FELux, you get a backlight, a bar light, and a spotlight. Kind of the benefit is you can get them larger in length and larger in size, and the spotlight has more intensity than our spotlight does. So if you need a specific form factor, CCS is your go-to. If you just need a larger light, FELux is going to be your go-to. So recommended lab units. If we were going to be building a lab and you came and asked me what are the basics that I should have so I can solve UV lights, solve IR lights, or solve SWIR applications. For UV light, I would recommend getting a 200 millimeter pure UV light. Not every application is going to need pure UV, but if there is an application that does need pure UV, you're going to want to have it to prove out the concept versus not having it. If your company is willing to spend a lot of money, great, get a UV and a pure UV light so you can test both, but if you can only get one light, I recommend getting pure UV to cover all of your bases. It doesn't mean you have to recommend pure UV if the light or the sample isn't extremely reflective, just, UV light will work. You can just recommend that even though you tested pure UV. For IR lights, we recommend having a backlight IR light. The FE backlight 200 by 200 850 is probably a good size. You can always go larger or change the sizes if you want. The flat dome light, the LFXV, we recommend that light a lot. The flat dome light is just a great light, but a lot of times when we're using IR light to solve an application, we're trying to remove print on a package that might be more reflective, and a flat dome light is great for that type of application. So the combination of the flat dome light plus the IR light often provides very useful and clean and not glared images. And a bar light, we would recommend the LDL 180 by 15 IR2 light. The reason that this is not an FE Flex IR light is because we want this 940 nanometers versus the 850 or 860. Not all the time will the different, 850 to 940 make a difference, but every once in a while you get a slightly better result with a higher wavelength. And so having the options of all three of these is just good to, like I say, cover your bases. If you would rather do an FE Flex, whatever length, 850, obviously do whatever you want, but having a good, 850, 860, 940 is a good overall fit for a lab. For SWIR lights, if your company is willing to spend the cash to get a SWIR set up to have in your lab, you got to find a good SWIR camera and lens. And then the lights we recommend are the FE Flex lights. You can do the FE Flex 10, which would be 200 millimeters, or the FE Flex 5, which is 100 millimeters. That's what we have in our lab. I put 10 because if I was going to ask for the lights, I would ask for 200 and then compromise and get 100, which is what happened. So ask for 10, settle for 5 LEDs. And ideally, you get one of every wavelength because that really is the best way. But if you're limited in what you can choose, I would choose 1050, 1450, and 1650. So at least you're covering the whole spectrum. You're just kind of missing the 12, 13, and 15. Wavelengths. And then controllers, get a PD4 to power your FELux or your CCS lights, or an FE power to power your FELux lights, or you can just get a 24-volt power supply for the FELux lights. But this is what we would recommend for if you're building a lab, the products to get. And we do offer lab pricing. So if you are, building up your lab, please reach out to your salesperson, tell them it's for a lab. They'll probably give you a little bit better price than you would get if you were just purchasing it for something else. So in summary, using UV versus pure UV light, I would say use pure UV light unless you need a specific form factor. But in the end, if your application isn't highly reflective, either one will work. If you're doing NIR versus red, choose IR light if there are workers nearby that you don't want to bother. Otherwise, the camera will have a higher spectral response at the red wavelength. So if there's no operator around that might get in the way, then I would select red. And if you have the option of using NIR versus SWIR, just save yourself the money and get an IR light with a standard camera, and don't try and get a SWIR light with that price tag and a SWIR camera and stuff unless you really have to. So that is the end. That is our webinar. We'll do a Q&A session starting now to help you guys solve your applications. Thank you.